Welcome back. Today we're going to start our discussion about vectors. I know that some of you have some familiarity with vectors, and so as we talk about this, we are going to be using some of the pieces to get us ready to solve some problems using vectors. And we're just going to look at what it means to have vectors. This shouldn't be an unfamiliar thing to you as we start to draw some things in the coordinate plane. And vectors, the thing about vectors is they have magnitude and direction. Okay, and we're going to talk about magnitude in just a minute, but magnitude is how long they are, and they go in a specific direction. It's not just walking a certain speed, it's going to a definite place at a definite rate. And when we draw vectors, just in general, this vector, if it has a notation that looks like this, this A comma B is called component form, and A and B are the components. Okay, so it tells you it's going a definite amount, right, for example, a definite amount up, and that's going to be its component form. So A and B are the components. So as we look at this, we have a point that they go to. So if a vector has, components of A and B, is going to go A to the right or A to the left. A to the right and B up is going to get us to a specific point. So with vectors, we're talking about a couple of different things, and we're going to see, that they form angles here. But the thing that we need to really remember is that in our notation, for example, if this was RS, this would be vector RS, so it's represented on top by a little arrow this way. R is the initial point. S is the terminal point. And you're going to recognize this this way that we name things from when we were talking about, unit circle, when we're talking about angles. And so all of these things are intertwined. They are related. And so as we look at components and we look at vectors and we look at how long they are and the direction that they go, we have to know that we have to look at the head minus tail rule. Let's say I didn't have this starting at 0. Let's say I had some other vector out here that was sort of just in space, and it was, T M, something like that. Okay, so Tm, it's in space. So how am I going to figure out? With RS, it's easy to say, okay, it starts at 0, 0, so it goes to the right 5 and up 3 or whatever. How are we going to figure out what the what the deal is with this one? How are we going to figure out what the magnitude is, or what the components are? Well, the head minus tail rule helps us with that. If an arrow representing a vector has an initial point of x1, y1. Okay, so this would be like x1, y1. And a terminal point of, you guessed it, x2, y2. So that would be up here, x2, y2. The vector is represented by and this is where our notation comes in. So we've got this, arrow form that tells us the components of the vector. And to find the x component, we're going to do x2 minus x1. And then for a y component, we're going to do y2 minus y1. Okay, and that's going to give us how far it is between these points. So for example, if this was 0, 0 and this is 5, 3, we know we'd go to the right 5 and up 3 because it would be 5 minus 0 and then 3 minus 0. But if this one's in space, then we have to figure out a way to do that. So that's going to be our general rule, the head minus tail rule. head minus tail, x2 minus x1, y2 minus y1. And so when we look at this, show that the arrow from R to S is equivalent to this arrow from P to Q. Well, how are we going to do that? Neither one of them, we don't have the component forms. And so what we're going to try to find is, what is RS? What are its component forms? Well, in order to find that, we're going to do -1 minus, minus 4, comma, 6 minus 2. And so that's going to give us 3, comma, 4. Okay, so it's going to go 3 right, 4 up. PQ is going to be equal to, we don't know yet, so let's figure it out. Let's figure out that component form using our head minus tail rule. So here we go. 5 minus 2, that one looks pretty good. And then 3 minus a -1. So we end up with 3, comma, 4. They have the same components, which means the vectors are equivalent. Okay, these are equivalent vectors. Let's talk about magnitude for a minute. So that's what component form is. That's finding the elements, the things that make up the vector. Magnitude is how long is the vector. Okay, so its magnitude looks like this. It's going to be the straight lines around V. Says, hey, how long is this? And so here is our formula. It's going to look familiar. So check this out. Looks a lot like the distance formula, huh? Because what we're dealing with here is we're dealing with a vector that has components that form a right triangle. And so our magnitude of our vector is going to be the distance between the two sets of points. Another way to do it is if V equals AB, notice we've already done the math. That's the x2 minus x1, y2 minus y1. So if we already know the component form, then the magnitude of V is equal to a squared plus b squared, and we take the square root. Okay, so having the component form allows us to do math more quickly. If we just have the end point, the initial point, and the terminal point, then we have to do a little bit of work. Okay, but that's magnitude. Okay, so let's find the magnitude of the vector V represented by PQ, and this should have an arrow over the top, where P is this and Q is this. So PQ, so the magnitude of PQ is equal to the square root. Now, I don't have component form for this, but to find component form, once again, it's related to our formula here. So I'm going to do x2 minus x1, so -5 minus a -3 squared, plus 2 minus 4 squared equals. So 5 minus a -3 would be -2 squared, plus 2 squared, minus 2 squared. Essentially, it doesn't matter because we end up squaring it. And so when we figure this out, we've got the square root of, this is 4 plus 4, which is the square root of 8. And we need to simplify this. So I can pull out a square root of 4. Square root of 2 is equal to 2 square root 2. So my magnitude of PQ is equal to 2 square root 2. Okay, just using that distance formula to find the length of that vector. Okay? How could we check our answer? To check our answer, we could use head minus tail rule and then redo our formula. Okay? But we've got our distance formula working for us right here. Okay. Vector operations. We can do certain things with vectors. Because they have magnitude and direction, we can extend them. So we can say, what about 3 times that vector? So it's a given length, 3 times it, or half of that length and distance. And so as we talk about scalars, we're talking about operations that we can do to vectors that involve multiplying them or adding them. And so the sum of two vectors. Okay, so the sum of two vectors, u, which is equal to u1, u2, not the band, and v equals v1, v2. When we take the sum, which would be u plus, and let me make that clear, u plus v, it's going to be equal to the x components plus the y components. So u1 plus v1, comma, u2 plus v2. Okay, it's pretty simple, pretty straightforward. We add those, add the component, the like components, add the x components, add the y components. If we were going to do the product, so for example, of a scalar k and vector u, this would be equal to k times u. K times u is going to be equal to k times u1, comma, k times u2. Okay, so it's like the distributive property, we distribute it in. So not only is the x component multiplied by the scalar, but also the y component is multiplied by the scalar. Okay, so other vector operations that we could do. In the tail to head representation, here's what happens. We're going to add two vectors. So if I have vectors u and v, if I've got a vector u and a vector v, tail to head says I put u in the coordinate plane wherever it goes. It happens to be on origin here, but if it's out in space, that's fine. And that's vector u. Tail to head says add v onto the end, so put the tail to the head, and then the answer goes from my initial point to now my new terminal point, which is at the end of both of the vectors. So this is u plus v. Okay? So wherever that point ends up, that's going to be u plus v. And I can write u plus v in component form knowing what point it goes to. Okay? The other way to do this would be to use a parallelogram. And what I can do is I extend u up here, so the same u, but I start at the same initial point, and I put v out in space. So this is u, this is v. And if I were to make a parallelogram, okay, so this is v also, and this is u also, my resultant vector is going to look like this. So this is u plus v. Notice it goes to the same spot. It's just the difference between putting them, head to tail here versus putting them out and then making a parallelogram and connecting them. There are advantages to each of the methods depending on what you're doing, but that's going to give us the ability to add u plus v and see it in space and find that resultant vector because we end up with a point here which is ultimately what we want, because that's going to allow us to find our component form and those sorts of things. Okay? Let's do a couple of vector operations. I'm given two vectors here. U, which is -1, 3, and V, which is 4, 7. What it wants me to do is find these component vectors, so let's do a little bit of addition here for this first one. So A is U plus V. Well, when I'm adding U plus V, when I'm doing U plus V, remember, it's equal to the parts of U, so if this is U1, U2, V1, V2, I'm going to add -1 plus 4, so it's going to be -1 plus 4, comma, and then add the y components, 3 plus 7. And so my answer is 3, 10. Okay? Next one, 3u. Remember, this is a scalar, so this is 3 times u, which is equal to 3 times -1, 3. And so it's going to be equal to 3 times -1, 3 times 3. So -3, 9 is my result. Okay, so this is the component form. I've got both components. I do my operations. I come up with my answer. This one involves doing two different things. The first one, I'm going to multiply 2 times u, so that's going to be equal to 2 times negative 1, comma, 2 times 3. And then to that, I'm going to add negative 1v, which is going to be equal to negative 1 times 4, comma, negative 1 times 7. And so I'm essentially going to have negative 2, comma, 6 plus negative 4, comma, negative 7. And so when I add those two things together, I get negative 6, comma, negative 1. And that's my answer. So do those two operations first, just like we would if we were doing multiplication, and then that gives us our basic, our two pieces that we're adding together, and then add them together like we would in a basic U plus V format. Okay. I know some of this is review, guys, but I appreciate you taking notes on it and making sure you got these basics down. Tomorrow we're going to go through the rest of this section, talk about unit vectors, do some applications, and look at what we can do with vectors. All right. Thanks for watching, guys, and we'll see you next time.